Good afternoon. So today we take up pyridine synthesis. Most of you have the first hand experience on the pyridine synthesis. Just like any other heterocycles, there are two broad approaches. One is directly you convert one pyridine derivative to the corresponding pyridine derivative, other is the ring constructions. Okay. If you follow the last few lectures, you will see I have been only just considering the constructions of the ring systems, okay, not the conversion of a heterocycle to another heterocycles or the vice versa. Okay. So, today again we look at pyridine synthesis, and almost all of you know the pyridine nucleus is everywhere. It is found in many important medicines, pharmaceuticals, agrochemicals, okay, biochemicals, like some of you probably know isoniazide. Isoniazide is a plain pyridine derivative, okay, and which is used as a medicine for tuberculosis. So, similarly, there are many medicines where you will have, or rather many biochemical compounds you will have the pyridine nucleus. For example, all of you know NADPH. NADPH will have actually pyridine derivative, which or sometimes actually it is a dihydropyridine derivative, and their corresponding analogues also are pretty useful. In many cases they are useful as a reducing agent or hydrogen transfer agents. Okay. And and likewise there are other, for example, there is a medicine called amlodipine. Amlodipine is a medicine for reducing blood pressure. So, that is also containing a pyridine nucleus, of course, that is a dihydropyridine nucleus. So, likewise there are plenty of pyridine containing important organic molecules. So, today we discuss about this one, and the way we proceed again, as I said before, you just look at this retrosynthesis, and there are two kinds. The first kind could be the condensation approach. This is well known to many of you, because condensation approach means where you just lose one small molecules, most likely the inorganic molecules. Then there is also another approach is known as cycloaddition approach, which includes Diels-Alder reactions, then 2 plus 2 plus 2 cycloaddition reactions, and in case of, and these there is just a small case, probably I think this is not of much use, but there is a reaction called Zincke reaction. Zincke reactions actually it produces the pyridinium compounds. Now, look at the pyridine retrosynthesis. Like before, what you do, you break open this molecule by hydrolytic cleavage. When I say so, of course, you have to target the heteroatom, in this case nitrogen. Now, when I say break open means actually you add water to it. So, and to maintaining this electronegativity. Now, if you have something like this, and then and what you do, you have to again break open this one. So, what you will find? You will find something like this, and then you will have NH2. So, NH2. So, like if you go on, if the next thing what you have to do, you have to break open this one, and if you do so, what you will find? You will find a molecule of this and plus ammonia. So, ammonia. So, what does it mean? It means that you can get pyridine from the corresponding diketo compounds 1, 2, 3, 4, 5, 1, 5 diketo compounds and ammonia, you can get to this pyridine. So, this is one of the ways to look at, and it has a name, Cronke reaction, but people no longer uses this. But the most important one, I think many of you know in this series is Hantzsch pyridine synthesis, right, iron pyridine synthesis. So, this is equivalent to the first one is equivalent to, so 5 plus 1 more, that means you have 5 atom systems and 1 atom systems. Hantzsch synthesis is many of you probably know, it is it contains well 4 plus, we will see that, let us say we will see that actually Hantzsch synthesis requires 3 components. One is the aldehyde, the other is an bit ester. In my notes you will find E stands for esters, then you have one more, so say beta ketoesters, and then an ammonia source which is ammonia. So, it is basically a 4 component reactions, it is Hantzsch synthesis. So, you can classify this as 1 plus 2 plus 2 plus 1 system, you can say. Okay. So, this is very popular. Then one more which is not probably studied that well, this is becoming a very important method of making pyrrole. So, in this case you take enamine, enamine, and in normally again this is E ester and acetylenic ketones, alkynic ketones, then alkynic ketones. This is equivalent to you can say what 1, 2, 3, 4, 5, 6. So, that means so it should be 3 plus 3 mode, and this has a name. This has a name. This is known as it is a natural products chemist, Bohlmann synthesis. So, better you remember as Bohlmann synthesis, because this is a very useful one, very useful one. And similar to this, there is also a method, which is equivalent to 3 plus 3. So, in this case instead of, that means what you do, you take this enamine system and which could be again ester, and instead of taking this acetylenic ketone. So, what you have to take? You have to take 1,3 diketones, 1,2 diketones. So, what you see here, this is just in a nutshell. Basically, there are if you look at some of the older literatures, you will find there are plenty of ways to break it, but the main objective is to just come up with the right synthesis, and almost all the cases you will see that the synthesis that would be well accepted is involving readily available starting materials, that is very important. Okay. And then you can go on changing this original version by improving the availability of the starting material, or by breaking into a simpler version. For example, one can simply think about this way without going through this hydrolytic cleavage. One can just think about, you just begin with a 1,4 dicarbonyl compound, okay, and like ammonia. So, it is equivalent to the one on the right hand side, but there is a little difference. You have to maintain this oxidation level. Okay. So, you know the calculation how to do this oxidation level. For example, in this one, if you condense this 1,4 dicarbonyl compound with ammonia, you will not end up with the pyridine derivative. So, you will get actually dihydropyridine derivative. So, you have to then oxidize the corresponding dihydropyridine derivative to pyridine derivative. So, and what else, like I have written so many things here, but you have to find out the commonality of all the approaches. What is common? All of them are giving pyridine, right? What is or pyridine nucleus? What else? All of them probably would be having a nitrogen. Yeah, that is also true. But as far as the approach is concerned, you see there are how many? I said, I think among all these Hantzsch is very popular. Probably you did not know this one. This is Bohlmann, which also is becoming very popular. And then this is the one on the left with 1,3 dicarbonyl compounds. It has a name, but I will not tell you. This is some GuRSC something nothing. Okay. But chemically, you have to find out that to develop a synthesis, you have to rely on a particular type of chemical compounds. Okay. Normally, if you go to the pyrrole and furan all other places, I mean will have this similar also starting materials. So, what could be the starting material? In amino ester. Well, if you do not need ester, then so you have to have enamine. But one thing, when I write here condensation, that means this belongs to a category called condensation. It must have a carbonyl group. That is important. So, all of these things are having a carbonyl group. Okay. So, but the approach is this way, that pyridine should be clipped into the corresponding hydrolytic cleavage product, that is basically amine and the corresponding carbonyl compounds. We will come back to and give you the examples. So, but keep it in mind that we will have a focus on Hantzsch synthesis and the Bohlmann synthesis. Of course, the other synthesis also would be exemplified. Okay. Then other possibilities, of course, cycloaddition. I think towards the beginning of the course, we talked about cycloadditions, right? Diels-Alder reactions and then 2 + 2 + 2 cycloaddition reactions. 2 + 2 + 2 cycloaddition reactions are useful in carbocyclic chemistry, but heterocyclic is not very popular, but becoming very I mean more and more popular because it is easier to handle and you just add them, you do not lose any byproduct. Okay. And then there are like say what are the catalyst? Cobalt catalyst. The other the latest addition is the rhodium catalyst, Cp2 rhodium chloride catalyst. So, like this there are nowadays some ionic rhodium catalysts also are being used to promote, and very recently we will give you one example maybe. Very recently I mean somebody has developed Diels-Alder reactions similar to this 4 + 2 cycloaddition reactions. Apparently, it is very easy to carry out. Once again, if you talk about the cycloaddition reactions, what are the different modes? I will not repeat much of them, but if you look at again the nucleus. So, there are ways to break, So, one of these ways would be simply you take and this and then something like this. That means, your 4 atom system is CCN system, CCN systems. Okay. Now, there are other possibilities also is there, other possibilities. So, this is one of these ways one can do. This other possibility could be I mean that this was the breakage here. So, you can cleave here also, right. You can cleave here, that means that would give you CNCC. Okay, CNCC. That means you have the nitrogen in a Bipyrdine position frame. You have the nitrogen at the 2 positions. Okay, and this has 2 equivalents. Many of you know where do you get this carbon? This is quite okay, right. So, this basically goes to if you have a conjugation things like this, and then oxime, hydrazine, all these things can be equivalent to an azadiene systems. So, that means all these Diels-Alder reactions should involve either one azadiene or 2 azadienes. Okay. Now, we have, but it is a very broad statement. Now, you have to go to the real life examples. For example, when I say CNCC, I think you have seen it before. Where do you see? Where do you get this 4 carbon unit or the 4 carbon synthon 4 atom synthon? You will get it in, and the last class we talked about though, right. Oxazole would serve 1, 2, 3, 4. So, if you have the right, that means this is a basically diene systems which supplies 4 atoms with CNCC. Okay. So, that means that can be used also for the synthesis of the pyridine nucleus. So, likewise, in one of the cycloaddition classes also we talked about something that the same thing can be obtained from a 6 membered ring systems. So, any idea where do you get it from? 6 membered system, that means, so you can get a 6 membered system, and then all of us know that Bogart's approach, nitrogen is eliminated. So, that means this portion would be eliminated, that means 1, 2, 3, this is the 4 atom systems, and if you place the nitrogen, this becomes CNCC. That means you can also make use of triazines for the Diels soda reactions. We have given examples before, and you can also look at today some of the examples. So, these are the two different modes. So, that was the first condensation mode, and the second mode is the, now it is a matter of just practicing things like this. Okay, let us look at the condensation approach. Condensation approach, we have said it before, and if you begin with a 1,5-dicarbonyl compound, now you want to convert into pyridine, right. So, what you have to do? You have to just simply ammonia, nothing else, ammonia, and what do you get? In this case, if you just do the shift base formations on one end, then other side you do, then isomerize. I think I do not have to explain to you, and you are all good now. Okay. So, you will get actually 1,4-dihydropyridine. Now, you have to know how to write dehydrogenate, then only you will get the pyridine. So, how do you get the pyridine? Dehydrogenate, and so there are limitations here. In pyridine chemistry, you cannot just randomly use oxidizing agents. So, that is the difficulty in heterocyclic chemistry. It is more difficult in, although heterocyclic compounds are not having chiral centers, especially aromatic ones, but they have other limitations. You cannot use all the reagents used in carbocyclic chemistry in heterocyclic chemistry, because of the propensity of this nitrogen to undergo oxidation. Okay. And so, the way one can do, how do you oxidize? So, the commonest one is nitric acid for some reason, common nitric acid, but there is a logic here. See, between pyridine and benzene, of course, all of us know pyridine is electron deficient. So, it does not undergo EG nitration, but it can dehydrogenate. So, or you can use nitrous acid also occasionally is used, and other one is CAN. Some of you probably know ceric ammonium nitrate. So, ceric ammonium nitrate. This sort of actually synthesis is useful for, let us say, a compound. I think I should write this structure, because some of you eventually would be taking this medicine at some point. This is a very popular medicine though, especially people like us, elderly people who are having the hypertension, they often take it, and almost every day I take one tablet on this of this molecule. This is called amlodipine, and here you write, I will write here E1 and E2, all of you know E1 for me ester. So, when I write E1, actually it is a methyl ester, and E2 actually ethyl ester, fine. And this one has another side chains where you will have these O and NH2. This is known as amlodipine. So, likewise there are quite a few marketed molecules which will have 1,4-dihydropyridine nucleus. Okay. Now, how do you modify this? I mean, actually see all these this is basically a modification, or you can say it is preambles for this Hantzsch synthesis. There are so many modifications. For example, you can take two components where first you do these Novaegal or aldol kind of reactions, and to get alpha beta unsaturated compounds, and let us say like this. So, that means if you have benzaldehyde and the corresponding ketones condensation product, then you take once again the previous example, like in the pyridine pyrrole cases, which is haloketones, then add ammonium acetate. By the way, in this case ammonium acetate is nothing but it is a source of ammonia. So, first it converts to ammonia, then the carbonyl is converted to this imine, okay, So, then I mean you can then imine can undergo cycloaddition reactions and eventually you will be getting this pyridine nucleus. I mean pyridine nucleus. So, in this case you will have all kinds of substitution here and there, and depending on the situations you may have this retention of the X or not depending on the reactions conditions. So, what it means that you do not have to have 3 different components, 4 different components, you can derivatize each of them, or you can just begin with an advanced intermediate and convert this into the pyridine. The other possibility is so this is the other, you can say sort of a variation of this one is this 3+3 3+3 mode 3+3 mode. And so, in all of these 3+3 modes what you will find this one of the components is a 1,3-dicarbonyl compound, 1,3-dicarbonyl compound. Okay. And so, now if you begin with an, as I said, a molecule of this kind and then take enamine, so you can easily predict the product of the reaction, right. So, what could be the product? I have what could be the product? Basically, you have to decide the, which bond would be first formed, that is most important. Okay. In say between the 2 carbonyls now, you have 2 carbonyls now, and which one is more reactive you think, and that would react with the amino group, the one next to ester. Ester, just like if you remember pyruvic acid carbonyl, pyruvic ester carbonyl is more reactive than the normal carbonyl groups, okay, because of this electron withdrawing nature. Like you have seen before that chloroacetone, bromoacetones, they are more reactive than the corresponding halides, the CH2 halides, okay, because of this that overlap of these electron in the transition state of the neighboring pi or anti-pi orbitals. Okay. So, that means this is what will be actually in the reaction then. So, what you have to do just invert this. So, it will be that means you react this one and this is E2, and so E2 would be reacting this now NH2 and this is Cn and this C, that means this would be condensing first here, right, and then via enamine reactivity eventually you will be getting this E2 here and this. So, you will be getting this. Okay. Now, I will just give another example. So, I mean this is a very interesting way of making the pyridine though. That means, in addition to the Hantzsch synthesis, the one that 3+3 mode also is very useful. I will tell you, I will give you one more example probably, or rather 2 more examples. Let us say with the same substrate, that means the 1,3-carbonyl here, and then you have this ester. Now, I change the enamine portion to a 3 component which will be looking like this. So, what it is that you have to remember. What is this compound? Actually, this is a very popular class of starting materials in heterocyclic chemistry, cyanoacetamide. Easy to make. You correspondingly take the chloro derivative, bromo derivative, cyanoacenes, and then amide formations. Very easy and fairly cheap. Now, if you recall that the previous example had this other part same. Now, now you have to again predict the product of these reactions. To do so, you have to first find out which bond would be formed first, that is important. In this in the previous case it was a free amine. So, free amine reacted with the most reactive carbonyl compounds, carbonyl groups, but in this case which one is likely under the influence of course, normally I mean a base is required, So, see here it is amide carbonyl, amide sorry amide NH2, amide NH2 is not a very good nucleophile, it is a poorer nucleophile. On the other hand, this one may have a carbonyl group, this may have a reactivity towards the carbonyl. So, that means this one would form first, and then once this is formed, automatically you know this is a pyridine synthesis. So, you will be getting the product here. This is this is cyano, and you have a carbonyl, and this is NOH, then this is E2, and so you will have this double bond, right, double bond up here and double bond up here. So, it is what you will be getting, actually you will be getting the 2 pyridone. No, that actually not taught. Actually, if you remember, those are the first classes last semester I taught. So, there are 3 different classes: pyridones, thiopyridones, and let us say aminopyridones. And what are the more popular tautomers? For pyridones and thiopyridones, this basically the keto tautomers are the more predominant, but for NH2 it is the corresponding NH2 tautomer is the more predominant. Okay. And let us look at one more variation of this one example. Let us say now what I do, I just do a small change here, and we move backward, and let us see. So, how to, let us say, make this compound. How to make this compound? I think this should be double bond, right? How do you make this compound? So, what should be the starting material? The mode is same, the 3 plus 3. Can you identify? Okay, okay. To help you, okay, the one that is that could be required again. To emphasize, the cyanoacetamide is the starting material. One of them is then tell me what is the other starting material, what is the other starting material, and the reaction condition that is used, it is KOH by the way, then KOH methanol and reflux. So, what could be the other starting material? 1,3 diketo compound, that is perfect, all right. Okay. So, acid chloride is not be a good reaction, because once you give KOH and methanol, it will hydrolyze to corresponding not ester, acid itself. Okay. Close, yes. If you take 1,3-diketone, fine, and then this should be ethyl ester. So, it should be ethyl ester. So, here you just get this condensation done, double bond, and then this carbonyl actually removes this, right. So, that gives you this one. Now, this very nice product. If you treat this with POCl3 excess, and normally it is done in a seal tube, so what you are likely to get? You are likely to get excess amount of POCl3. It is a standard protocol in hydrocyclic chemistry. If you have pyridones with hydrogens, you get corresponding these dichlorides, So, you get cyanide here, chlorine and chlorine, as if this is just like a phenol, acid chloride OH is replaced by chlorine in by POCl3 reactions or PCl5 reactions. So, here also if you tautomerize it would look like it is a dihydroxy compound, it is a dihydroxy compound OH and OH, and this OH is replaced by carbonyl chlorine, and so you got these compounds. Now, there is a series of reactions I think maybe I think it is worth knowing here. Let us say we want to remove this chlorine and then convert it to the corresponding cyano compound without chlorine. So, how do you remove this? How do you remove this? Basically, it is a process called dechlorination, dechlorinations. That means, you have to look for a right reducing agents. There are not many, but in heterocyclic chemistry hydrogen is good enough. Hydrogen is good enough. This sometimes stannous chloride, tin, all these things are fairly okay, but in this case. So, if you use hydrogen and unlike simple palladium, this palladium chloride has been used, and then palladium chloride is used and the sodium acetate is used to I think you can understand why sodium acetate is used, because in the hydrogenolysis of this carbon halogen bond you generate HCl. So, HCl should be neutralized by the base sodium acetate. Okay. And the palladium chloride, of course, all of you know under the influence of palladium under the atmosphere of hydrogen, palladium chloride is reduced to palladium 0, and that hydrogenolize the corresponding carbon halogen bonds. Okay. So, I think that gives you some of these ideas about the Hantzsch synthesis, the modifications, or you can say the 3+3 versions. And next, of course, is very popular to me, at least or it is liked by me. This is the one what I said, it is Bohlmann synthesis, and this is sometime carried out in one step. Requirement is same as before, but in this case it is a 3 atom is the 3 atom system is enamine or the enamine, and so you will have R group here, R group here. The other part is a 3 atom part, that you have to remember. So, what could be the variation? Normally the variations are in case of heterocyclic chemistry, what I said before, that you have to have a carbonyl compound, right, and if you want to change a compound or a substrate, you make this carbonyl compounds with the corresponding acetylenic derivative, because acetylene is equivalent to a carbonyl group. All of us know that it opens up or rather hydrolyzes to corresponding in ketones into the presence of mercuric sulfate catalyzed hydration. Okay. So, this is an enamine, so it is in the ketone derivative again, and then this was discovered long back in 1957 by Bohlmann, and so you begin with acetylenic carbonyl compound. So, you have to remember this much, this is very important. As I will proceed, I will give you more and more examples, you will see very unique reaction though, very easy to carry out once you have the right substrate. So, and in a case like this, just heat at 50 degree centigrade in ethanol, and I think all of you can guess what would be the product. The product here in this case what else? So, what is it? What is the product? This product is basically a Michael addition product. So, that means just very mild condition 60 degree is a Michael addition product, but this Michael addition is not the heteroatom Michael, it is a carbon Michael type of reactions, as if the enamine nitrogen is pushing the electrons to the carbon and then adds to that, then goes on. So, and then this was the original condition. Then this intermediate is heated at 120 to 170 degree centigrade, 170 degree centigrade. You can guess what happens under the reaction conditions. It gets isomerized to the right direction. That means amine now is transposed, not transposed, okay, comes to the other side, and then this trans double bond now go to the cis double bond, and so you have this system. Then all of you can guess, once you have an amine and ketone, it is very easy to cyclize. So, and come up with the right product, and what you will be getting? You will be getting this now NH here, OH here, and then the rest of the things are in order and like this. And so, as usual, the aromatization is the driving force, and so you get nicely well defined substituted pyridine derivative, nicely well defined substituted pyridine derivative. So, this is the format. Okay. And specific example, like say once again enamine means you have the beta keto ester corresponding enamine, let us say E2 means ethyl ester, and then just take the corresponding propagylic ketone here. So, not I should not say propagylic ketone, acetylenic ketone, and then just like that the previous this is the 50 degree first, and then in ethanol, then this high temperature heating, high temperature, and you get this pyridine derivative. And the yields are fantastic. In the first case it was 98%, in second case it is 87%, it was 87%. So, this is here, I mean after doing all these things here, but the Bohlmann reactions are very useful. And then the same reactions when carried out with silyl protection, is a TMS group, and the other part remaining same, you get the same product, but the yield is again very high. In the first step it is 98%, and the second step it is 100%. So, you get the same product. So, with silyl protection, okay, we will have more example. For example, more example, I think let us say, I think one more example probably. Next example basically tell you that if you have, you do not have to make this enamine, okay. You have to just take this right ketone and the right acetylenic compound, the ketone up here, okay, you can put R everywhere, here and there, does not matter, and then take ammonium acetate, ethanol and reflux. What it means? You have just simplified these reaction conditions, simplified, that means you do not have to have the enamine pre-prepared enamine. Take the ketones and the acetylenic ketones and this ammonia source, you straight away in one pot you will get this pyridine derivative. Okay. Now, there are other ways. So, let us say and why this is so popular, I think I will give you one or two applications. Maybe I will give you one more examples where you can divert this reaction to a pyridine derivative. For example, if you take initial Michael addition product, which is a conjugated diene system with enamine, right, conjugated diene system, you have R and then this R here. Can you recognize what it is? This one is nothing but an enamine system here, and then propagylic ester, okay, condensation product or addition product. then if you treat these with NBS methanol, so you get NBS methanol and sodium methoxide, you can divert these reactions into a pyridine derivative. Can you guess what could be the product? I said before pyridine derivative, sorry, a pyridine derivative. So, what is the starting point? What reaction can you think of? NBS methanol is a source of bromonium ion. So, bromonium ion, that means this lone pair would direct this bromination here, right, bromination here. Then you have in the system sodium methoxide. So, sodium methoxide, and eventually what you will be getting, let us say, so R double bond, then this again NH R. So, initially it would form first this corresponding bromo derivative, and then what? Then it will isomerize. All these things would be isomerized like the previous example, that amine would come on this side, right, the carbonyl on this side, then this double bond would move, this bromine would move here, again thermal isomerizations, then you have this ester here, and then nitrogen would now attack the carbonyl of the ester group. So, you will be getting here R here, then it is a pyridine derivative. So, pyridine derivative and the carbonyl up here, this is R, again this is R, this is R. So, essentially what it is now, it is not a pyridine derivative, it is a pyridine derivative, Okay. Let us look at two, I think I have two examples to show you about these applications of these reaction, and let us see the first one and then we will see the second one later, maybe towards the end of the class. Let us say if you have a problem like this, it is a very complex molecule. This was required in the program of a total synthesis of a very gigantic molecule, gigantic thiopeptide. Thiopeptides are nothing but cyclopeptides with sulfur, and you have a pyridine nucleus here, and the other portion is a thiazole, and on this side one more 5 membered heterocycle, and this is also a thiazole, and then okay, maybe I will write this, this will have oxazole now, oxazolidine with this, and then this. This is just a small molecule though, this I mean compared to the total synthesis I will be talking about. This is actually, there is a name called Bagley. So, this is Bagley's synthesis, I would say, and it has been published in 2007, but what we are concerned about the structure, how to make this pyridine 2,5-disubstituted pyridine, 2,5-disubstituted. Obviously, the obvious option should be you take this enamine, this thing, that thing, we go back to the Hantzsch synthesis, but the authors have preferred this Bohlmann synthesis. So, Bohlmann synthesis, that means what do you need then in the Bohlmann synthesis? Corresponding enamine, right, enamine. So, in this case the authors have taken enamine. Okay, so the enamine, let us say from the left hand side. So, this was the enamine on this side, right, and so if you, that means it is an H2 up here, and oh I see, okay, sorry, I think I made a mistake here, there is an ester here, okay, that is the reason I missed, okay, there is an ester here. So, now you can guess. So, this is E2. So, you have to take E2 here and E2 and so enamine and what else 1, 2, 3. So, that means you cannot take this one, right. What else you have to take? You have to take these 2 carbons should come from the acetylene and the other one, this carbon comes from ketone and that is it. So, that means the life is easier now. That means if you have in retrosynthesis based on this Bohlmann, it is pretty easy. It just only thing you have to remember, you have that the starting point is acetylenic ketone and enamine. Acetylenic ketone is first and this. Then just look at the structure and just do this all these things. Although apparently it looks simple, but getting the substrate itself requires so many steps. This one took some 9 steps, the other one took 11 steps. Then, but once you have once you know the process is very easy, just mix them and heating it. In fact, the reaction was done once again in ethanol, and so once you do this ethanol reaction and like before you can do this what ethanol actually assists these first steps, that is the cycloaddition. Then cycloaddition is done by either heating or by different reagents. In this case there are many kinds of reagents. I do not have the list here, there are many other kinds of reagents, but the one that is popular is iodine. So, if you just take 20% of iodine once again in methanol and the cycloaddition takes place and you will be getting the right pyridine derivative and this as and then this. Okay. So, we will go to the next topic or next subtopic. What is the next subtopic? Diels-Alder reactions. Diels-Alder reactions has been taught before, but the plain Diels-Alder, that means one adjunct diene systems. One adjunct diene system was not very popular or not readily available. I will just give you one instance where a alpha beta unsaturated ketone has been converted to diene system. Like if you begin with the sort of a pyruvate ester and then hydroxylamine, and the next thing is the sulfinyl chloride. It is not a sulfonyl chloride, by the way, it is sulfinyl chloride. There are 3-4 different kinds of the acids where you have in the. Okay. So, you will be getting here corresponding oxime, and then this actually first it forms, right. I will not write the whole structure, you can guess, I guess. So, this on reaction with sulfinyl chloride, very interestingly it undergoes sort of a disproportionations and it gives you this sulfonamides. This sulfonamide is produced and this is in this case this is now E2 here. So, that means one aza bipyrdines are not very easy to make. Okay. So, that is the reason why the Diels-Alders are not very popular. So, the people are going towards the organometallics approach. So, I will give you one more example later, and then this require a particular now what is it, dipolarophile, I should say dipolarophile is this one, that means it is tetraoxygenated, and one can guess the Diels-Alder means 6 membered ring. Then you will have the all kinds of the substituents here and there. Obviously, the purpose was a total synthesis. Then here you had this sulfone or sulfonamide part. Then if you treat this with BF3, So, you get oxygenated pyridine now, dioxygenated pyridine. So, which is nothing but this ester here E2. Okay. So, what is the lesson? The lesson is that the Diels-Solder reactions are not very common, but under certain cases you can do it. And alternative is only published this year, very recently, in last few months ago. There was a paper by Rovis and it is published in 2013 and JAX, and what is it? It is again a kind of an oxime. Now, this oxygen has been linked to PIV. PIV means Pival-oil group. Now, if you take again an alkene systems, that means the other two pi system, and the base is used here rhodium Cp star and chloride. So, it is a dimer of this, and heat it at only around 85 degree centigrade. Very interestingly, in one pot you will be getting the pyridine derivative. That is unique, that this is published in JAX because of this simplicity, such a simplicity. Only thing that you have to, of course, choosing the right catalyst also requires a lot of experience, insights about the reaction mechanism, etc. If you go through the reaction mechanism, what you will find, the last carbon nitrogen bond is being formed. Last bond that is being formed is basically the carbon nitrogen bond. So, that dictates the substituents to be here are adjacent to nitrogen, then rest of the groups are wherever it was required, it is there, are there. Okay. And the R in this case, of course, electron withdrawing group, and which is ester, carboester, it could be amide, it could be carbonyl, or sometimes it could be even aryl. So, it is a very versatile reaction, Okay. Let me give you just a last example. This is a very fascinating example, though. It is somewhat like the Bogart's approach. If you begin with a triagent system, you will have, let us say, a triagent system like this, E R, let us say E2, and in this case it is a pyridine. Now, you just heat with non-Bohlmann system, and what do you expect? You expect a reaction, of course. What is the reaction? The reaction is, if you mix them together, so there are basically you have a binuclear system, right, two different heterocyclic system, and you have a pyridine here and a triagent system. So, according to Del Bogart, the triagent systems are good dienophile, good dynein, that means it 4 electron component. Okay. And but normal system double bond is not that activated, but it is an inverse electron demand Diels-Solder reaction. That means it is electron rich double bond, this diene part is electron poor. So, it will undergo again a 4+2 cycloaddition reactions, and in this case obviously, so you can write this 4+2, this ester would be here, the nitrogen double bond, now nitrogen, and this double bond. Then you have pyridine nucleus now, right. So, it does not stop here, all of you know, once you have a double bond nitrogen. So, there would be a retro-Diels-Solder reaction. So, what you will have? You will have like this double bond here, right. Then you have again a diene system here, the nitrogen and E2, and a pyridine nucleus would be hanging at the bottom. What next? I think it's quite obvious to all of you, right? What is obvious next? So, it does not stop there though. See, basically whenever you see a double bond, a reaction is under thermal conditions, you have to think about retro-Diels-Solder reactions. Even cyclohexene would undergo retro-Diels-Solder reactions, give you butadiene and ethylene. So, we see a double bond up here means the allylic bond would be cleaved, allylic bond would be cleaved. So, in other words, what you will be getting? You will be getting this cyclobutadiene and a pyridine nucleus, right. Now, the bottom pyridine is now blown up and it would look like this, and you have E2 ester. So, what did you achieve? You achieve 2 prime bipyridine derivative, and is it a big deal? Is it worth doing? That is important. You have see when you do chemistry, you have to justify yourself. The chemistry that you are doing is important, useful. Okay, is it useful? Organometallic chemists, right? See, once you are organometallic chemist, ligand. That means, in fact, if you can produce 2 prime bipyridyl, let us say in a lower price, you will be rich. It is very difficult to make. What people do, if I remember correct, it is done by some oxidative coupling of pyridine under the influence of palladium something to the percent of 5%, 10%. Okay. And of course, all of us know that 2-bromopyridine is not easy to get by, right. So, I mean you have to develop some other methods. This is one of these ways how one bipyridyl can be synthesized. Okay. And last reaction, okay, it is not that important as I said, but most of the textbooks will have this. It is known as Zincke reaction. Zincke reaction is nothing but what you do, you begin with dichlorobenzene, sorry, dinitrochlorobenzene, and then take pyridine, you get the actually quaternizations of nitrogen. So, you will be getting NO2 up here, NO2 up here, then nitrogen plus, chlorine minus. Now, if you treat this with excess ammonia, sorry, excess amine, okay. So, what you are likely to get is something like this. This nitrogen does not belong to this pyridine nitrogen. Now, it is basically this nitrogen comes from the corresponding amine, and the mechanism suggested is that it opens up to go to this kind of conjugated triamines with NH and pH, and this is chlorine minus. Okay. So, then R NH2 again, just like typical nucleophilic substitution reactions, it will go like this and then recyclize to corresponding alkyl pyridinium salt, this is known as this. So, summary, in the previous thing long back during the cycloaddition reactions, we talked about a lot of things, and in general there are 2 modes, condensation and cycloaddition mode, but there are other possible synthesis could be. What are the other possible synthesis? 3+3 kind of annulation, that is 3+3 kind of annulations, but all of them will have the ketones, but the Diels-Solder reactions will not have. And there is also a method which is not talked about, but it is not very popular, that is called, all of you know, RCM, ring closing metathesis. Ring closing metathesis is not very useful in the case of aromatic pyridine chemistry. It is useful, but that would give you the what is called non-aromatic heterocyclic compounds, bipyridine derivatives, etc., etc. And there are many times if you have a carbonyl group, this RCM is not really very predictable. Okay. So, that is the reason I have not talked about that, but so to close this lecture, I think we should remember that Bohlmann synthesis is a very good synthesis. Bohlmann is very